Okay, so N means moles, all right? And so if we take all three of these facts, since they're all equal to V, we can then say that V on the left side is proportional to N, so N's on top, and T, and inversely proportional to P. So you get this relationship here where volume can be kind of, it's not equal to NT divided by P, but it's proportional. That means if volume goes up, then so does the entire term on the right hand here. In order to get rid of this proportional thing, this little fish looking thing, we have to multiply by a proportionality constant. So in this particular case, the proportionality constant that we use is called R, and it actually comes from the slope of those graphs we saw from Charles' law and Boyle's law, which is a really cool experiment to find. If you do all these different experiments, you know, one of them monitoring volume and temperature and another one doing volume and pressure, and you get the same slope, that's remarkable. R has a lot of different units, and so here's this table on the right is from Wikipedia. The one we use the most often in chemistry for our purposes is right here, and it's in terms of liters and atmospheres and moles. So that is the best choice for us because it'll help us if we have a pressure and a volume. We can use that. So this R thing is just a constant. So all I have to do to go from a proportionality to an equals sign is put R as a factor here. So now the equation becomes V equals R times NT divided by P. Now, we don't really like things in the bottom of a fraction, so instead, we're going to multiply both sides by by P. And we get this equation, PV equals nRT. This is called the ideal gas law. And it's a kind of a combination of Boyle's law, Charles' law, and Avogadro's law. The variable P is pressure. The unit is almost always in atmospheres. So if I get a pressure that's not an atmosphere, I know I probably have to convert it right away. V is volume, almost always in liters because gases occupy a lot of space. N is the number of moles of gas, not total moles. There could be solids and liquids there. They don't matter. The thing here is just gases that matter. R is the ideal gas constant, which we had on the prior page. It's just a number. And T is, of course, temperature, and it's always in Kelvin. So generally, I have kind of a three-step process for gas problems. The first thing I do is to write what I know, including the units, okay? You always want units, because the units will save you from messing up how you rearranged an equation. So I write what I know. I identify what I don't know. So what's the question looking for? Then I check my units. I need everything to match the outline I just gave you, atmospheres, liters, moles, and Kelvin. If it doesn't match, I convert. And then finally, I apply one of the equations, either the ideal gas law, which works almost all the time. That's the best bet, actually. Or perhaps the combined gas law, Charles' law, all these different possible laws, okay? And I rearrange it if I need to, and then I plug the variables in. Okay, so here we have a problem where it says determine the volume of a gas occupied under STP. So standard temperature and pressure. STP, we need to remember this, STP specifically means that the temperature is 0 Celsius, which is the same thing as 273 Kelvin. And the pressure is 1 atmosphere. it also tells us that the number of moles is exactly 1 mole of gas. So the only thing I don't have here from the ideal gas equation is R and V. R is just a number. That's a 2 there. So that means if R is just a constant, then the only thing I don't know is V. So then I'll use the ideal gas equation where I want V by itself. So I'm going to divide by P on both sides. So I'm going to come down here. I'll have to erase it in a second so we can answer that question. But for now, it's okay. So we get nRT divided by P. And I plug it in. So 1 mole times 0.0821 liters times atmosphere per mole K. Now I know you're going to be very tempted not to write the units of R. You need to, because they must cancel out, or you have used the wrong equation, or maybe rearranged incorrectly. So make sure you're writing all your units. And then T we said is 273 Kelvin, and P is 1 atmosphere. So again, before we calculate anything, let's cancel what cancels. So everything where there's something on the top and the bottom of the fractions. Oops, not liters. I meant moles. Okay, so we're trying to find volume, and we get liters out of that. It's the only thing left. When I put this in my calculator, I go 1 times 0.0821 times 273. That equals 22.4133. I divide by 1 atmosphere, which of course leaves it at the same value. So the V, let's see here. I don't really have defined significant figures because STP is a defined temperature, but I guess we'll pick 273 as our limiting. We also have 3 in the R value that I picked. So I'll just go 22.4 liters. And this is the exact relationship that we predicted from before. We said that the conversion factor for a gas at STP was 22.4 moles per liter. So good, we've just proven that. Okay, so if you still need to write some things down on your notes, be sure to pause it at this point and do that, because I am going to erase it. All right. So the next problem says that we have a pressure of 740 torr. So I'm going to assign that to pressure. I feel like we probably have to convert that because we said that pressure is usually atmospheres. But we'll do that in a second if we have to. And then it says a temperature of 35. I definitely know I have to convert that one because we said that is always in Kelvin. So I'm just going to do that real quick. So we get 308 Kelvin. And a volume, I cut my page off. Hang on. Okay, so it says a volume of 1.5 liters. So we're going to go with that. And it's looking for how many moles, so moles is N. So I think we have everything we need again to use PV equals nRT. This time I want to get to N, so N is right here. So that means I have to undo R and T, so I'll divide by R and T. So my equation becomes N equals PV is on the top, right here, and RT is on the bottom. Oh, and R again is still the same number, 0.0821 liter atmospheres per mole K. I don't expect you to memorize R. I'll always give that to you. All right, so we just plug it in. Oh, but if R is in atmospheres, then torr has to be in atmospheres too. So it turns out we do have to convert that. So we're going to do that by looking up the relationship between atmospheres, which is what I'm trying to get to, and torr from prior slides. So we go 740 divided by, because the atmosphere is on the bottom, torr is on the bottom, and we get 0.974 atmospheres. So down here, 0.974 ATM times the volume, which we said was 1.5 liters, divided by R, and times T on the bottom. Whoa. Not 30K, 308K. Obviously that's different. So atmospheres cancels because I have one on the top and one on the bottom. Same thing for liters. And I have K on top of the denominator, and I have mole times K on the bottom there. So when I have a fraction on the bottom, that means it becomes the top. So my unit here will be moles. All right, so we get 0.974 times 1.5, and so that's 1.46 divided by the bottom, which is a total of 0.0577 moles. We have two significant digits, so I'm just going to write 0.058 moles. Okay, so sometimes we might want to calculate the density of a gas. So if you're interested, this originates from the ideal gas equation, where we just rearrange so that pressure is on one side. Basically, we want to get moles per liter by itself, because this is molarity, right? Moles per liter. And so you can rearrange it like this to get moles per liter. And once you have that, you can use the relationship between moles and the molar mass of something, because if N times the molar mass here gives you mass, that means I can substitute and put mass into my equation here, because moles is here. Okay, so basically the bottom line is, if I want to calculate the density of a gas, I use this equation, and it's derived from the ideal gas equation here. Density is still mass divided by volume. Typically for gases, we use grams for mass and liters for volume. Again, because gases occupy so much space. Over here, the pressure is still in atmospheres. Molar mass is always units of grams per mole. That comes from the periodic table if I know what the gas is. Okay, so I just add up all the elements in the gas and get grams per mole there. R is the same as it was before, and T is still in Kelvin. So basically, if I know what the substance is, I can calculate grams per mole, and I can plug it in there. That gives me the density. So this is a relatively easy way to figure out what the behavior of the gas you have is going to be. So we're going to use the same equation. So density equals the pressure times the molar mass divided by RT. And so to assign these variables, oh, we got CH4, so that tells me what the molar mass is. It's going to be the weight of a carbon plus 4 hydrogens. So it's roughly about 1605 grams per mole. So now I know what the molar mass is. And then, let's see, at 110 atmospheres, so that's my pressure. No, not 110, 1.10 atmospheres, that's very different. And 25 Celsius, so that's temperature. Again, the very first thing we're going to do with this temperature is to convert it by adding 273. So we find out that the temperature is 298 Kelvin. And they give us the R right there. So all we got to do is plug it in. So the density equals 1. We don't even have to rearrange this. It's already exactly how I want, because the question is asking me for density. So It's on the left all by itself. And we're ready to go. Okay, and then on the denominator here we have R. And we have the temperature in Kelvin, so 298. Okay. Again, we're going to cancel what cancels. So atmospheres on the top and the bottom. Moles are actually on the top and the bottom. Kelvin's on the top and the bottom. So we end up with grams and liters. And we said that that's a typical density unit for a gas. So when I enter this in the calculator, what I get is 1.1 times 16.05. So the top is 17.655. And I'm going to divide it by the whole bottom, which is 0.0821 times 298. And I get 0.722 grams per liter. Okay, so that's an example of how you would find the density of a gas just by knowing what the gas is, the pressure, and the temperature. We can rearrange this equation to figure out the molar mass of a substance. This didn't line up the way I wanted, but